Hello everyone. So this is the third video lecture in this series. So last Friday we had talked about weight updation in neural networks, but I think due to time constraints I was not able to explain the concept very clearly. So today I'll go over linear regression and gradient descent to make the learning algorithm a bit more clear and intuitive. So let's start off with linear regression. So linear regression is a supervised learning algorithm, which means that we train it using a dataset that includes input values or the features and the corresponding output values or the ground truth. The goal is to model the relationship between the inputs and the outputs so we can so that we can make predictions. So the term linear here refers to the model's assumption that the relationship between the input features and the output is linear. In other words, we are not using any higher power terms of the features. Higher power terms, I mean terms with power greater than 1. So basically, the model predicts y as a straight line combination of the input features. And the term regression, it comes from regression analysis. It was coined by Francis Galton. He was doing a study on the heights of people's offsprings. So he made a conclusion that, the heights of the offsprings, they regress towards the mean height of the population. So from there, we get the term regression. In essence, linear regression estimates the best fitting straight line or plane in n dimensions if there are multiple features that minimizes the difference between the predicted and the actual values. So let's understand this with an example. So imagine we are trying to predict housing prices. Our dataset has two features, x1 and x2. x1 is the floor space in square feet, x2 is the number of bedrooms, and the output y is the price of the house that it was sold for. The price clearly depends on x1 and x2, but we need to figure out how much influence each feature has, right? To do this, we assume a simple model or the hypothesis that looks something like this. So h of theta x equals to theta naught plus theta 1 x1 plus theta 2 x2. So theta 1, it's a constant or the bias term. Theta naught is the constant or the bias term. Theta 1 is the weight or contribution of floor space to the output value. And theta 2 is the weight or contribution of the number of bedrooms. So this model is linear because the relationship between x1 and x2 and y is a linear combination. So no x square or x to the power n, where n is greater than 1, is being used in this hypothesis. So visually we can imagine plotting different data points, x1 and x2, on the 2D plane. So our goal is to find the function that fits as closely as possible to these points. So we are basically minimizing the average distance between the data points and the line or the plane that represents our model. So if we stick to this linear form, where we are not using any higher powers of x beyond 1, the model is called linear regression. But if we start including higher powers of x, like x squared or x to x cube, then we get something called polynomial regression. But for simplicity, let's focus on linear regression in this case. So now we have our hypothesis, but how do we optimize the weights, theta 1 and theta 2? To get the best fit, we need some updation algorithm, right? Now we have our hypothesis, but how do we optimize the weights, theta 1 and theta 2, to get the best fit? So this is where gradient descent comes in. So gradient descent is an iterative optimization algorithm that adjusts the parameters to minimize the error between our predictions and the actual data points. To measure this error, we use a loss function. In this case, we are using mean squared error. So j of theta 1 comma theta 2, j is the loss function, which is parameterized by theta 1 and theta 2, is equal to the average of the difference between the predicted and the actual value of all the samples in over a single iteration of the whole data set. That's what this whole equation means. So the square ensures that the error is always positive, and we could also use mean absolute error, MAE, by replacing the square with an absolute value, but MSE is more common. One more thing about the notation, the I in the notation, I within the bracket in the notation, represents the ith data point in the training set. For example, x of 0 would mean the vector 1000, 3. over each iteration, we calculate the difference between predicted and actual values for all data points, average the results, and we use that to update theta 1 and theta 2. This process continues until the model converges to the best approximation of the data. Now that we can calculate the loss per iteration, here is the updation mechanism for the weights or parameters of the hypothesis j theta. So here goes the updation rule as per gradient descent. For every iteration over all the samples in the data set, we compute j theta, which is the loss function, and we update the j theta, theta j, as the previous value of theta j minus alpha times the derivative of the loss function with respect to the j theta. This derivative basically computes a slope or the rate of change in the loss function with respect to the j theta, theta j, or the jth weight in the matrix. So we are updating the jth weight based on the change it brought about in the loss function. Alpha is the learning rate, and you can think of it as a multiplier that stabilizes the updation. So we can look at it visually. So say the loss function j of theta, it depends only on one theta, say. And so maybe we are somewhere here in the curve at the moment, at the current iteration, and we can see that the slope is positive. Then by gradient descent, the updated theta will move towards its left, towards the local minima, right? The importance of alpha is that suppose the slope were too high, then the updation would be drastic. It could go further away from the local minima, and j of theta, the loss function, it would jump around, never being able to converge completely. One more thing, the updation is simultaneous. Here is the correct algorithm. So we compute temp1 and temp2 first, independent of each other, and then the assignment is made to the weight parameters theta 1 and theta 2. To make things more clear, here is a wrong implementation also. So we compute temp1 first, and we update theta 1 also after that. And this updated theta 1, it reflects in the j of theta in the next step, which is for theta 2. So this updated theta 1 is used in j of theta while computing temp 2, and this temp 2 basically gets assigned to theta 2. So this is something that we should not do. This updation is not a chained updation, it's basically a simultaneous updation. This is something that we must always remember in gradient descent. Just to wrap it up, think of gradient descent think of it visually in terms of like standing on a hilly terrain. The peaks represent high error or loss, and the valleys represent the low loss. So your goal is to get to the lowest point or the global minimum. The slope of the hill at any point is like the gradient, right? It is the gradient. So it tells you how steep the terrain is and in which direction you should move. The updation rule essentially means that you take small steps in the direction that brings you closer to the valley at the fastest possible rate. Where the gradient is highest, the gradient is highest towards the minima. That's basically what it is doing.